All right. Happy Wednesday, everybody. I hope you all had a really good long weekend. Couple of announcements. We've got a homework to return to you.
Yeah, they are alphabetically ordered by last name. You just grab one from each packet and then you pass it up.
Okay. Other announcements. I've been getting a lot of emails regarding like, oh, I wasn't able to turn in my homework, or I couldn't come to class, or anything like that. Just a reminder, it's stated in the syllabus, but I'll say it again. There's no late work accepted in this class. It's not reasonable for Marissa Bell to have to go back and grade things late. She sits down, grades everything all at once. So regardless of the reason, I don't need to know. You don't need to tell me. We're just not going to turn in late work, okay? To account for life, because life happens, I will be dropping assignments, a few scores at the end of the semester to account for things like that. So it'll all work out in the end. Other reminders, there's no recitation today. Your quiz has been on Blackboard since Monday. It's due on Friday at the beginning of class. As with everything, no late work accepted. So if you're not going to make it to class on Friday, regardless of the reason, and you want to be able to have that quiz graded, then you better email it to me in advance, okay? There will be a regular homework assignment due on Friday. Your first test is in 8 days. So hopefully you've been doing your homework carefully and doing the reading carefully, keeping in mind that we're focusing on concepts and process, not just trying to get to the final answer. If you've been doing your homework with the mindset of let me just get the answer and be done with it, then you're not doing yourself any favors. Okay, that's not the ideal way to be preparing for a test in this class. Okay. All right, let's see what else. I've got my random list of names. Don't be surprised if your name comes up twice in a row. So yeah, I don't know. It was really weird trying to randomize names, but I think I did it. I think I did it well. So I'll be calling on you to participate in class. And last but not least, bring your laptop on Friday. We're going to start working with Graphing Calculator. So if you haven't gotten that set up yet, then you should, and bring your computer on Friday. Okay, so are there any questions or concerns at the moment? Yes, ma'am.
Regarding the homework, is there a specific format that you would like us to take? Because so far I've been printing it out and turning in all the pages and just kind of writing on it.
Okay.
Or would you prefer like a lined sheet of paper, like a sheet of paper?
What you're doing is acceptable as long as you can make it look professional. Okay, right, so it should be clean, clear, concise, coherent, full sentences in your thoughts. Marissa Bell, do you have anything to add to that?
No, it's okay. I'm writing.
Okay.
But as long as it's clean and I can read it.
Yeah.
It's fine.
Don't make her work too hard to read your handwriting. That's a noteworthy thing to take with you all throughout life, okay? The harder you make people work, the less likely they are to do things in your favor, okay? All right, so I'm going to take attendance while you do a quick review. So I want you to take these covariation bars, and I want you to talk about what will happen if I push the blue bar out to about here. Where will the red bar go? And I want you to explain your answer in 2 different ways, okay? So that's what you're going to be working on while I take attendance, and you should have already passed your homework to the middle if you haven't done so. Okay? Go ahead and do so now. All right, Ahmed. Anthony? Kaiser? Rudger? Adam? Jackson? Jan? Ankita?
Here.
Elena? Yumeng? Bethany? Teddy? Payun? Yeah. George? Taylor? Annabelle? Moises? Daniel? Was that a here? Okay. Kyle? Sarah.
Here.
Taylor. McLean. Matthew. Lauren. Penny. Taylor. Wait, what? Was the first Taylor here? Yeah?
I think I'm the second.
I think you might be the first one. What's your...
Jotcom.
Yeah, you were the first one. Okay. Scott. Ryan. Horatio. Frank. Shelly. Eiley. Ailey? Wait, Eiley. Okay, I had it right. David. Q. Justin. Anna. Anna? Anna. Sorry. Nathan. Jonathan. Oh. You almost got marked absent. Okay. Darren. Ruby? Taylor. Shackelford. Okay. Philip. Susan? Miranda. Renee. Dakota. Riche. Jessica. Madeline. Ashley. Joseph. Caesar. Harrison. Nayeli. Courtney. Jeff. Help me out. No? Not here. Okay. Maxwell. Oh, how do I say your name again? I know, but how do I say your name? Jafu. Okay. Maxwell. All right. Ariane. Katya. Christopher. Excellent. Okay. Alrighty. So I want two different explanations. So Taylor Davis, be here? So can you give me one explanation of where the red bar will land and why?
Well, I don't know, it's kind of difficult to tell how
Okay.
how large that blue bar actually grows, but because the two were related to each other, the amount that the red bar will increase will be proportional to the amount that the blue bar will increase. So I'm thinking maybe somewhere either beneath or past where your mouse currently is.
Okay. So somewhere over here, maybe?
Yeah.
Okay. Can you expand on what you said, though? Like, how did you get that?
Well, as you modify the blue bar, the red bar will change as well because they're both
Okay.
both roll.
Kyle Green, can you help?
It looks like it will take approximately 4 red bars to equal one to get to the point, the limit at the top for the blue bar.
Okay, so you're saying it'll take 4 blue bars
4 red bars,
for red bars
right?
to do what?
For the blue bar to reach the demarcation line, I guess that's what it is, at the top,
So you're saying it'll take 4 red bars
approximately.
to make the blue bar go that far?
Yes.
Jackson, can you help me understand what's happening? Jackson. Hi.
What he's saying is that if you extend the bottom red bar
Uh-huh.
4 times what it's currently at,
Okay.
the resulting change in the blue bar would put it at the demarcation line.
Okay, so remember, I moved the blue bar first, right? I said, I'm going to move the blue bar, right? So how much do I stretch the blue bar by to get to there? 4 times? I've been hearing 4 more than I've been hearing 3. So we'll write 4. Okay, so then what should happen to the red bar? It will also be stretched by a factor of 4. What have we done here? What kind of reasoning is this? This is scaling, right? Okay, that's one way to think about this. Okay, Daniel Flores. Do you have another way that you could explain this? Okay, so So what's the reverse way of saying that? Because remember, I'm saying I'm moving the blue bar. So I want to start with the blue bar. So to get from the blue bar to the red bar, what happens? How do I get from there to there?
I would, the red bar would be more, or 4 times the size of the blue bar.
Oh, that's inconvenient. Okay. This 4 is definitely different than the first 4 that I wrote. Okay. So how do I talk about that in terms of relative size? Daniel, you're off the hook. Horatio.
So the blue bar is 4 times as big as the red bar.
Is the blue bar 4 times as big as the red bar? Which one's bigger?
The red bar is bigger.
The red bar is bigger. Okay. Adam. Adam B. Bossum. I would like to know how you can talk about the blue bar and the red bar in terms of relative size.
So, like now, if our growth is going to be constant, or if the blue bar and the red bar are always going to be constant, the red bar will always be like 3 times the size of the blue bar.
Okay, you say 3 times?
3, 4, something like that.
3.5. We'll make the numbers different. Okay, that's fine. So the relative size of what is, let's try Darren. Are you here? Darren? No? George, Don. Yeah. Can you give me a whole sentence? Relative size of blue bar and red bar.
For every 1 unit you move the blue bar, the red bar will move 4 units.
Okay, so I don't want to concentrate on movement at the moment. I just want to talk about size. Relative size. Yes, ma'am.
The blue bar is 1/4
Okay. Madeline? Are you here? The red bar is, okay. So I've written a number 3.5 on the, let's work with the number that's on the screen. Okay. You got a way to say it?
I think so. So the blue bar is always going to be, well, the red bar is always going to be 3.5 times bigger than the blue bar.
Okay.
So then if one increases, then it's always going to be 3.5 times bigger.
Okay, we're getting there. You want to,
If we let the blue bar represent 1 unit,
uh-huh.
how many of those units make the bottom? So 3.5.
Okay. So the relative size of the red bar is 3.5 times the blue bar. Yeah? That's what I was going for. You should be able to give that back to me, okay? So using that thinking, when I move the blue bar all the way out to here, when I extend it, right? So if I actually move, whoa, doing cool things. I don't know what I just did. Nope, it doesn't like me. Ah, doing really crazy things. I don't know where it went. Where did it go? There it is. Shoot. Nope, did it again. Hold on. I want this one. This one. Okay, so if I move the blue bar out to here, right, then oh, I have a fancy thing. Never mind. Forget that. Don't look at what I just did. Then if I think about the relative size, we said the red bar was about 3.5 times the size of the blue bar, right? So if I move the blue bar out to here, then how will I figure out where the red bar lands? Do you want to say that louder? So am I moving the red bar 3.5 times this size?
The size that it is.
The size that it is?
Yeah. No, it's 3.5 times the size of the blue bar.
So currently the red bar is 3.5 times the size of the blue bar. That relationship should be maintained. So when I move the blue bar out to here, the red bar should land 3.5 times further than that. So somewhere over here. Right? So from here to there, that's also times 3.5. This is relative size reasoning. Yes.
Can you explain that one more time?
Yep. So presently, right, the blue bar, or I should say, it's easier to say, the red bar is 3.5 times the size of the blue bar. Okay? So if I change the size of the blue bar to now be up to here, then the new red bar should be 3.5 times the size of that. Okay? So imagine that the blue bar comes all the way out to here, right? And so now the red bar, ooh, crap, I don't know what I did. I'm sorry, guys. I'm still getting used to this technology. So then how did it get so small? Epic fail, epic fail. You have a question, go for it.
When you say you want two ways to look at it, you're talking about relative size right now.
Yep.
Explanation of relative size in
Yes.
one way.
Yes,
The other way to look at it would be
scaling.
scaling, which is each quantity separate.
Yep. So, okay. So, let me run through this one more time. Hopefully I won't press any buttons wrong. Okay. So, relative size. Blue bar to red bar. The relative size is about 3.5. Okay? So, the relative size of the red bar in terms of the blue bar is 3.5. Okay? So, if I stretch the blue bar out to here, then the new red bar should be 3.5 times that length. Okay, so, here's another one, 2, so here we've got 1, 2, 3.5, right? So it'll be somewhere around there, okay? So this is where the new red bar will go, okay? And that is, again, taking this value and looking at the relative size of the new red bar in relation to the new blue bar. Okay. The other way that we could look at this is to say that if I move the blue bar to here, okay, then I'm scaling it this way, right? By now I'm only doing it by 2.5, right? So then the red bar, I should also scale it by, there's another copy and half of a copy. So it'll land here, right? So times 2.5 to get to here. Okay. Yes?
So for speed, you would do it 2.5 times the red bar, not the blue bar.
Right, exactly. So scaling, we're sort of looking internally, right? So the blue bar, I scaled by 2.5, so the red bar I will scale by 2.5, versus looking at blue bar relative to red bar, old blue bar relative to old red bar, and then new blue bar relative to, new red bar. Okay? Okay. So, all right. What I want to do now is take a look at something that you guys have probably seen before, okay? So what are we looking at here? What is this? Some type of function? Can we say anything else? What did we talk about last Friday? Ooh, that was a long time ago. Yeah. It's a collection of points. What's the term that we use for that? Is that a line? A graph, right? So last Friday we talked about what is a graph, right? What constitutes a graph? And so when we look at this image, this is a collection of points, okay? Now, if I were to put a point here, right there. Oh wait, what did I just say? Does that sentence make sense? If I were to put a point here, am I putting a point there? Is it already there? Yeah, it is, right? So I'm just highlighting a point at the moment, okay? So then, depending on what we know about our axes, we could then describe what this point represents, okay? So it represents some quantity on the x-axis. Why are you giving me a hand? Some quantity on the x-axis relative to some quantity on the y-axis, right? And this point collectively shows the relationship between those two quantities, okay? Now, if I change the value of x, what happens? The value of y is going to change, right? So in terms of your reading for today, what kind of language could we use? I got away from my name list. Arian? Yeah. Input and output, okay. Susan, do you have other words from the reading? Your neighbor wants to help you. Yeah.
What is it? Uniqueness or independent variable?
Okay, so independent and dependent, right? So what did we change? What did we have control over? The x, right? So originally I had this x value here. I changed it to this x value over here. Did I have a choice in what y value came along with it? No, that value was predetermined, right? It was determined by the x coordinate, okay? All right, so now if I can get, this back up, and let's do that. Okay, so now what I want to do is ask you guys to compare how these bars, as I let them vary, relate to the graph that you're seeing on the right. Is that big enough? Whoa. Hold on. I did it again. Where'd it go? Mark, can you remind me how to get this graph back into normal shape? I need the vertical axis. Yep. No, the other one. But I don't want the x-axis so small.
So when you do this, you can you do option, it'll only zoom on the x-axis. If you do command, it'll only see it up and down.
Okay.
So you want to do it
I want to zoom out on the X.
out on the x.
Yeah.
Maybe zoom in on everything now.
This is good.
And then also, when you're playing this, if you do option play, it'll only go forward and it'll start over instead of going back.
Oh, cool.
So when it hits, it'll just start over.
Okay. Cool. Thank you. All right. Sorry for the technical difficulties. I'll be teaching you how to use this program on Friday. Yay. Okay. So, what's the relationship? Is there one? Yeah. How do we explain it?
So the red bar would be the independent variable,
Okay.
and then the blue bar would be the dependent variable.
Okay.
Moving down the x-axis, the red bar increases and the white bar increases and decreases accordingly.
Okay. So I like what you said a lot. The one thing I want to modify is the use of the word variable. I just want to make sure that when we use that word, that we are really thinking about quantities. Okay. I'm not inherently opposed to the word variable. I just want to make sure that when you use it, you are thinking of a quantity that you can actually measure. Okay. So, but that's exactly right. So what kinds of things can we do to see that these two representations are actually the same? Well, you remember my fancy trick? I can take my blue bar and I can stack it with the red bar. So now it actually traces out, right? And then I can keep track of where it's going. Now my axes are scaled differently, which is what accounts for the different look of the graph, right? But I don't want to mess with that at the moment because I'm going to practice before Friday. Okay, cool. So, but again, the takeaway here is that we have the same relationship being represented in two ways, right? One way is using our covariation bars, and the other way is via a graph, okay? So that brings us back to this main idea, okay? Covariation. So in your brain, what does this term refer to? Because if you type this word into like a Word document, it'll underline it in red squiggles, right? This is our word. This is our like powerful word. So what does it mean? Let's see. I was on. Did I call him Miranda already? Miranda. Yeah. Yeah.
The way I think of it is how two quantities relate to each other.
Okay.
So if one, with those bars,
Mhm.
the graph, the blue bar represents the y-axis. So when it would go back, it's because the x-axis was moving along, increasing faster than it was decreasing.
Okay.
So that's how they were related.
Okay. So I wanna take what you said because there's lots of goodness there and modify just a touch, which is to say that when we looked at those bars, we were looking at two quantities that were both changing simultaneously, okay? And that's what we intend when we use the word covariation, okay? How does that relate to what we've talked about so far in this class? Not just today, but all last week. Yes?
The two, like the two bars,
Mhm.
is showing how they're two separate quantities,
Mhm.
but how they change with each other.
Great. Good. Yes. What does that have to do with calculus? Everything. That's right. Good. Okay, so covariation is how two quantities change together. Okay? Now, I want you to remember, though, the first day of this class, I gave you a whole long spiel about how everything in this class is going to be related. We're talking about concepts, right? So you're going to be introduced to ideas in groups. So what have we done as a group? We have discussed multiplication and division, right? The basics of changing quantities and measurement. Then we looked at visual representations of how two quantities can change together. We did that via horizontal bars, and then we just did that with graphs, right? So now you want to move into symbolic representation, okay, not just visual representation, because there's power in symbolism, okay? And so what is the means of doing that? Function notation, okay? So that's where we're headed. Okay, so let's go back to our, ooh, just kidding. Let's go back to our bars. Oh, I do have to figure this out. Oh, no, I don't. Ha. Cool. Okay, so let me make our function a little bit easier to work with. Let's make it that, okay. And okay, so what have I just done? I have changed my function, so now we're looking specifically at the function f of x equals 1/4 x. So let's talk about what that means, okay? In particular, right now, just in terms of what we've done before, what does that mean about the sizes of the red bar and the blue bar? It looks a little funny because the axes are not scaled properly. Yeah. Right, okay, so let's tackle this one more time. How can I use the phrasing relative size? How do I explicitly get across relative size? David Q.
Say that the red bar has a length that is 10 times the size of the blue bar.
Or 4 times, yes. The axes aren't scaled evenly. Yeah. Okay, great. And then if you wanted to do the reverse, so the blue bar is 1/4 the size of the red bar, right? Okay, great. So now let's actually tackle a symbolic representation of this idea. So you guys have probably all seen this. Nope, hold on. Here we go. This notation before in previous math classes, right? So I want to break it down. Okay, so the f is what we call the name of our function, okay? The x is called the input variable, right? In your reading, it was referred to as the input, also the independent variable, right? It's the thing you get to choose. You get control over it, okay? Now, the whole expression, f of x is how we read it, is the output, right? So let's go back and give some, well, okay. So I already typed in that the function we're looking at in this graphical representation, this visual representation, is the function whose rule is take 1/4 of your input, okay? So this thing on the right-hand side of the equal sign is called the rule, okay? All of that together is the function definition. Imagine you were to open up the dictionary, right? And you look up a word, you've got the word, and then you've got like, oh, it's an adjective or whatever, and then you've got everything that explains what it is. That's what we're doing here, okay? So I'm telling you the name of a function, and I'm telling you everything you need to know explicitly about that function. Now here's the power of function notation. If I were to erase this rule, I could still talk about the function f, okay? And f of x will still represent some output, okay? So don't be fixated on having a rule, because sometimes we're going to talk about functions where we don't know the rule, okay? But this rule is simply the set of instructions that tells you what to do that tells you how to get the output given a specific input value. Handwriting did not get better over the weekend. Okay. All right. So this is the language. This is the vocabulary. We've got the name of a function, the input of a function, we've got our entire output, and we've got the rule. Now, some of you might be asking yourselves, but I always see something written like y equals f of x, right? Whenever you see a graph, you usually see that kind of notation. So what's happening here? Okay, so now we're saying let this variable represent the output values of our function f. And so then we can create our axes to then draw a visual representation of what's happening. Okay? Fantastic. So, okay, so once again, let me highlight a point on the graph. Let's say maybe, oh, I don't know. Is there a good one? That's an easy one. Right here. Okay. If I highlight that point, because the point was already there, remember, the whole graph is a collection of points, then I could describe what this point means if I were to, for instance, say that x was, I don't know, the number, let's go back to this volume example, number of milliliters of water in a bottle, and y is the height of the water in centimeters, okay? So then if I highlight this point, what ordered pair is this? 1, 0.25, right? Now, we were able to determine that ordered pair because we had the rule. Do you agree? So if I know that the input value is 1, then I can plug 1 in for my input, right, f of 1, and compute what the output should be, okay? Now, in terms of the values that I've given to x and y, how would I explain the meaning of this point? Yes, sir.
So for every 1 milliliter of water in the bottle, 0.25 centimeters height of water in that bottle.
Okay, so what you say is technically true, but it's not precisely what this point is representing. Because you said for every 1 milliliter.
So for 1 milliliter.
Mm-hmm. So when there is 1 milliliter of water in the bottle, the height of the water in the bottle is 0.25 centimeters. Okay? Okay, let's pretend for a second that I don't know what the rule is. Okay? And now I mark this point over here. Can I still label an ordered pair for this point? Yeah? How? I heard, who said yes? Yes. Just look at it. I'm looking. Okay. Can somebody, let's see, where were we at? Jan?
You would take the value of the x,
Okay.
that's the value of the y.
So I can definitely see, I don't know if you can, that the x-axis is at about 1.8. Okay. Do I know exactly what the y-axis is? I don't have a very good scale over here, right? But can I be precise about what the value is for the y-axis? I see some people nodding their head, yes. Daniel? Flores? Were you one of them? No? You want to take a stab at it anyways? Do you want to take a stab at it anyways? Okay, so I don't have the rule, but can I still be precise? You want to help him out?
Did you take a point from the first 1.25 use that relationship between those in order to find that point?
Ah, well, so remember, graphs can be deceptive. This looks like a straight line, and we're going to talk about how that would yield the result that you're talking about. But I don't know that about this function yet. Yes, sir. Ah, I can be precise about what the output value is, right? Because I know the input, and I know that I'm graphing the function f of x, so the output value will be f of 1.8. That's as precise as you can get, folks. Okay? But we can, so this is the point though, this right here, f of 1.8, represents a value. Okay? It represents the output of the function when the input is 1.8. Okay? So in terms of milliliters and centimeters, can somebody take a stab? How about Rutger? So how can I interpret this new point, 1.8 comma f of 1.8, in terms of milliliters and centimeters? I don't know that. Okay, so let's see. Matthew Jones, can you help him out?
So for 1.8 milliliters of water in that bottle,
Uh-huh.
you're gonna have a height of f of 1.8 centimeters.
Exactly. Okay, so when there are 1.8 milliliters of water in the bottle, the height of the water in the bottle is f of 1.8 centimeters. Okay, that is the meaning of this point. Okay. Okay. All right. I didn't leave a whole lot of time, but I have a present for you. We're going to talk about functions in depth in this handout. Okay, so take one, pass along as fast as you can. As soon as you get a copy of the handout, start tapping. Did everybody, did the homework make it around to everybody but Alex? Okay, if you don't have the handout in front of you yet, I've got it on the board so you can start thinking about the question. Okay, so we've got a function A equals P of W, where W is the water height in a swimming pool in meters, and A is the area of the water surface in square meters, okay? Why does this relationship meet the criteria for a function? So from the reading, you guys read about what a function is. Justin?
So for every input of W, there's a unique output of A.
Okay, right. So like when you fill up the pool, right, to a certain height, it can't have two different surface areas. Plain and simple, right? So there's a unique area corresponding to each height, right? Okay, what's the name of the function? Is the name P of W? It's just P, right? What's the input? W. What's the output? So I heard P of W and I heard A. Which is it? Anybody want to make an argument one way or the other? Yes, sir.
PW is the output.
Uh-huh.
A is the process function.
You want to try?
They're both the same.
They're both the same. Okay.
Because P of W is going to represent the output
Mm-hmm.
of whatever the rule is, and that's what A is, which is equal to P of W.
Yeah, we said they were equal, right? So P of W is absolutely the output of this function. This function being the function P, right? But when we defined the scenario, we said let A equal P of W. So A is a new variable that I'm introducing to stand for the output, okay? So both are correct, okay? Which of the quantities is determined and which is independent? So independent is W, dependent is A, right? Fantastic. Okay. Here's where we really get to the heart of the matter. Each expression below represents an unknown value. Although these values cannot be computed because no rule is provided, right? I didn't tell you how to compute P of W. I just told you what P of W represents. So each of these expressions has a meaning that is precisely defined, okay, by the notation. So explain what the meaning is in terms of the language related to the swimming pool. So P of 1.8. Rashay?
The meaning of P of 1.8 is stating that that is the area of the water in meters squared when the height of the water in the swimming pool is 1.8 meters.
Great. So let me say that P of 1.8, because that's what you said, right, is the area of the water in square meters. That's perfect. Awesome. What about the second sentence? So I call something that looks like P of x equals 14.3 a mathematical sentence, right? P of 1.8 was an expression. Now what does this new sentence represent? Let's see. Annabelle? Are you here? I don't remember calling that in roster. Oh shoot. Shelly. Yes.
Saying that the area of the water source is 14.3 meters squared.
Okay. So
Or that's the output then?
so the area of the water's surface is 14.3 square meters. All the time? x meters, right? Because these are, x represents something, right? It's a quantity. It stands for the height in meters, okay? All right, what about the next expression, okay? P of 0.9 minus P of 0.7. So I said minus out loud. I want you to give me the actual meaning. So not using words like subtraction, difference, those don't give me meaning. I want to know what this actually means. Did you want to?
We are, what that equation will do is it will give us the change in surface area of the pool.
So the change in surface area of the pool when the height changes. Awesome. Okay, so that whole quantity, let me, again, it's that whole quantity represents, ooh, that got interesting. See if I can make that not look like that. So here it is. It represents the change, right, in surface area. Okay. Awesome. We are on a roll. We're also out of time. So what I want you to do is, I'm going to add this to your to-do list for Friday, because, you know, why not, is to finish this worksheet, okay, as well. So, alrighty. Have a wonderful afternoon. Okay. And if you did not get your homework, you should do that. If you showed up late, you should tell me.